Okay, so this week our task was to characterize a Lego dart gun that we were given, which means like measure the initial velocity with which it fires its dart, and then use that information to ensure that our dart gun hits a target at a given X distance away. So to do this, we used a dart gun, a launcher, and an iPad, and the video physics app that's on those. So first we had to find the initial velocity with which the gun fires its dart. So to do that, we fired the dart directly upwards, and then we tracked its path with the video physics app on the iPad, and we used the data recorded from the app to find its initial velocity of the dart gun. So from the data collected, we calculated that the maximum Y position was 0.9828 meters above the launch height, and that it was at that maximum Y position 0.469 seconds after the launch. So using these values, we can calculate the dart's initial velocity, which was 4.394 meters per second. Then we were given an X distance that the dart would have to travel to reach our target. So yeah, just a like how far away it is. The essential thing that we had to do to ensure that the dart hit the target was to get it to launch at the right angle. And though we know VI, the initial velocity, if the dart is shot at an angle that isn't 90 degrees or flat on the ground, which it won't be, then the X and Y velocities are not going to be the same as the initial velocity, VI, but we can work them out using trigonometry. Woo! So SOHCAHTOA is the thing that can tell you the relationship between launch angle, your VI, VX, and your VY, and this is what we used to find VY and VX, and it helps if you visualize it like a right angled triangle, because that's just trig. So now that we know our equations for VX and VY, we need to find an equation for the launch angle for a given distance that the dart has to travel, so that's our X value. So we're given this equation 1 for final X position, i.e. where it will have to land to hit the target. Now, by rearranging that initial equation for Y position that we had a few slides back, we can also find a value for time using the values that we already have. And I won't show the derivation for that because that'll take a long time. But we end up with equation 2, which we can substitute into equation 1 to get equation 3. So given that we have all the values for every symbol here in equation 3, all we need to do is rearrange to find the value of theta that we need and then sub in our values. So we ended up with our launch angle, which was 13.59 degrees, and it worked. Our dart hit the target, which is very exciting.